Okay. Um, First, this is an announcement. Our first midterm will be on November 3rd, Wednesday. So that will be 2 weeks later. And the time is at 10 o'clock, okay? 10 o'clock, not 10:10, up to 12:20. And the coverage will be chapters 1 to 3. Okay, so I will finish chapter 3 before the midterm examination. And this is a cross-book examination. Okay, but you are allowed to bring one sheet of A4 paper. Okay, and you can write anything on both sides. Okay, I will make a formal announcement through the EE class platform. Okay, any questions about the first midterm? Right. And as the TA wrote a note to you that for every quiz you have to sit you will sit in the classroom. Otherwise, you will be considered as absent from the quiz examination. That means that your grade will be 0. Okay, it has been asked by the university that we have to ask every student to be seated in the right seat. All right, before it's the control of COVID-19 pandemic. So. And so we have to take pictures of you to make sure that you are sitting in the right place, okay? Because last time, many of you didn't follow the instructions. I'm not so, I cannot understand why you can't follow the instructions. Because examination is a serious matter for you. So when you are asked to sit a certain place, you have to sit that place exactly. Okay, because that happened just a few days ago. Tia told me this matters, but I think this is a very serious offense, you know. So you have to take these things seriously. So that's why I want to say it at the beginning of my lecture. Okay. All right. So the next theorem is a useful one for you to construct a linearly independent subset in a vector space, 1 by 1. Okay, so it's kind of a good procedure for you to learn. All right, so suppose that X be a linearly independent subset okay, so X is a linearly independent subset of a vector space V. So the vector space can be a generic vector space, not necessarily Euclidean vector space. Now, if there is a vector in the vector space and this vector is not in the span of the set X, then we are sure that the union of this set with the singleton V means that we can add the V into the set without destroying its linear independence. Okay, so that this union, this bigger set, is also linearly independent. So before before I prove the theorem, so I want to make a remark. The above theorem can be used to construct a linearly independent subset in a vector space. All right, so I would like to use a diagram to show it. Suppose that this is the vector space V here. All right, and here is the zero vector here. This is the zero vector. Okay. To construct a linearly independent set, right? You can pick up any arbitrary non-zero vector V1 here from the V. Because if you pick up the zero vector at the beginning, then you get a linearly dependent set already. Okay. So that first of all, you have a V1, which is non-zero, because it's different from the zero vector. So the zero vector is here, and this is V1. And now V1 span a subspace. We have shown before the span of any subset is a subspace of the vector space. So the SPAN V1. All right, so it span a subspace big. Right, so out of the subspace, the span, you pick up a second one. So you have V2 here. All right, you have V2. And then V1 and the V2 will span a bigger subspace. Okay, so this one is the span of V1 and V2. Okay, and at this moment, by the theorem, V1 and V2 form a linearly independent set. Okay, all right, and then you pick up a third vector V3 out of the span, and you get a bigger one. So this is the span of V1, V2, and V3. Okay, and etc. So if you go further, right? You go further. And you find that you have Vn here out of this one. And so this is SPAN V1 up to Vn minus 1. So suppose you have to select the Vn minus 1 vectors there. Okay, and out of the span of the first n minus 1 vectors, you get the Vn. And finally, you find the span of V1, V2, up to Vn. All right, and you find this is equal to V, and then you stop. Because once you get this condition, then out of V, you don't have any vector, all right, to pick up. And so you stop. Okay. Okay, so this is the quite occur oftenly. But if you can continue to do so, then you can do it indefinitely. Okay. Okay. So it's possible that you will do it. This is just one of the possible situations. Okay, so any questions about this procedure to construct a linearly independent subset in a vector space? Okay, so here is the proof of theorem. So the theorem is 2.4.11. Yeah, sorry, I forgot to put the number of the theorem. Okay, so the approach is use the to prove by contradiction. Okay, so we suppose that the union is linearly dependent, right? So this is the approach we have. So there exist distinct vectors u1, u2 up to in the set. Okay, such that a1 u1 plus a2 u2 plus plus am is equal to 0. So this is a linear relation. Okay, and for some scalars a1 a2 up to am, not all zeros. Okay, so that means that we have a non-trivial linear relation in the set, the union. This is it. All right. Now, so we must, so in this m vectors, we must have ui equal to v for some I, right? Otherwise means that all the ui's are in S, but X is a linearly independent set, so this is a contradiction. Okay, because for a linearly independent set, we can't have any non-trivial linear relation. Okay, in this set. Okay, so that otherwise it would be in S, and plus am is a non-trivial. It's a non-trivial linear relation. Okay, on S. So which is a contradiction. To the linear dependency of S. Okay. All right. So now we know ui for some I is equal to v. Also, we must have AI. So AI is the corresponding coefficient of UI. Okay. So we must have AI not equal to 0. Why? If AI is 0, then we can just remove the ice term. So now the rest becomes to a non-trivial linear relation on S, and which again a contradiction. Okay, so that AI cannot be 0 again. Right? So otherwise, A1 U1 plus A I minus 1 UI minus 1 plus AI plus 1 UI plus 1 plus AM UM is a non-trivial linear relation on S. So a contradiction too. Okay, so we know AI is non-zero. So now we have the situation. We move alpha I UI, but UI is equal to V, right? Already. So alpha Vi is equal to minus A1 U1 minus AI minus 1 UI minus 1 minus AI plus 1 UI plus 1 minus AM UM. So divided by alpha I, because alpha I is non-zero, so V can be expressed by AI AI minus 1 AI plus 1 divided by AM divided by AI UM. So this is in the span of S, okay? Because it's a linear combination of vectors in the set S. So it's all right, and now it's a contradiction too. Why? Because in the theorem we know that V is not in the span of S. So a contradiction, right? So we start with this premise that this union is linearly dependent, and we find ourselves that no way to go, because we will go to contradiction. Okay, and so we conclude that S union of V is linearly, so that means that the original premise here is incorrect, and so the conclusion is that this union is linearly independent. Questions? All right. We talked about linear transformation from an Euclidean vector space to another Euclidean vector space. But linear transformation can be a function from a vector space to another vector space. So here we redefine linear transformation in a general setting. So we let V and the W be two vector spaces over R or over C. Okay. Yep. I have asked you to read Appendix B on complex numbers. So that the scalars now, if the scalars are real numbers, then the two vector space over R, and if the scalars are complex numbers, then V and W be two vector space over C. Okay. Okay, so a function T from V to W, okay, is called a linear transformation right? If T alpha U plus beta V is equal to alpha T U plus beta T V for all vectors in the domain V and scalars alpha and beta. Okay. This relation is called linearity of the linear transformation. Okay. So actually it's called linear transformation if the function T send this linear combination of vectors U and V to the same linear combination with same coefficient alpha and beta, but the vectors will become to the images of U and V by the function T. Okay, so that is this one. So let T from V to W be a linear transformation from a vector space V to a vector space W. Okay. Now to justify that T is, oh, I'm sorry, be a function, I'm sorry. A function. First we know it's a function from, sorry, from a vector space V to a vector space W. All right, now T is a linear transformation. If and only if for all vectors in the domain V and the scalars alpha T U the V equal to T U plus T V. Okay, so the image of the sum of U and V is equal to the sum of the respective images of u and v. And the image of alpha times u is equal to alpha times the image of u. Okay. So we can split the checking of this linearity by checking that that is additive in this way, and that it will conserve the scale multiplication. All right. So this way. So the forward path is quite easy. We look at the right. So this is by the unitary property. That is axiom 7, right? So we use the unitary property, the axiom 7 of the vector space. So this is become 2 by linearity. T. And so this is again by the axiom 7 is a unitary property. Okay, so we have that. And T alpha u equal T alpha u plus 0 times V. Okay. Equal to 0. So this is axiom 3. Okay. With 0 vector, and this is T alpha u plus 0 V. Okay. And we know there is a theorem tell us that 0 times any vector is equal to a 0 vector, and so we have alpha Tu plus 0 Tv. Okay, again alpha Tu plus the 0 vector, because 0 times arbitrary vector is 0 vector, and this is equal to u. So this is axiom 3 again. Okay. So this is linearity. Maybe I will find this is the theorem number for that. Okay, so that is theorem 2.4.4. Okay. Okay, so this is the forward part. Now the backward part. For the backward part, plus beta V. Okay, so we regard this is as the addition of two vectors. All right, so we have alpha u plus T beta V. Okay, by using the additive property, and then by this scaling property, this is alpha Tu plus beta Tv. Okay, so we have done. All right, so this theorem is the checking of a function to be a linear transformation. Okay, so let V1, V2, Vn be a linearly independent subset of a vector space V, and we know that V is actually the span of this set. Okay, so suppose that we know this information. Okay, and let W1 W1 W2 Wn be arbitrary vectors in a vector space W. Alright, so we have two vector spaces. One is V, the other is the W. And for V, we suppose that we find a linearly independent subset, right, such that the V is just the span of this subset. Right, then there exists a unique linear transformation T from V to W such that we have the following correspondence. The image of V1 is W1. The image of V2 is W2, etc. The image of Vn is Wn. Okay. So now, the importance of the theorem is it tells us how to construct a linear transformation in a very, you can say that free way. All right. The only thing is you have to make sure is that if you want to construct a linear transformation from V to W, okay. Now, if you are able to find a linearly independent subset of V such that V is equal to the span of this linearly independent subset, then you can arbitrarily select n vectors from the codomain W. Okay. So, and then you just require that the image of V1 under T is W1, the image of V2 under T is W2, etc. up to the image of Vn under T is Wn. Then the theorem guarantees that there is a unique linear transformation satisfy your specification. So you think about that, this is just a specification. Okay? All right, so let's see a proof of that. By theorem 2.4.6, a theorem proved last week that because this is linearly independent, all right, and the span of this linear independent say is V, so that each vector U in the domain V has a unique representation as a linear combination of V1, V2 up to Vn, i.e. U can be written as A1, V1 plus A2, V2 plus A and Vn with the coefficient A1, A2 up to An are with the coefficient uniquely determined. Okay, so U can be represented as a linear combination of the vectors in this linearly independent subset, and the coefficients A1, A2 up to An are uniquely determined. Okay, that is from theorem 2.4.6. All right. So we define, because we want, the theorem says that there is one and only one, means there exists a linear transformation. So there is one and only one linear transformation satisfy this specification. Okay, so we have to construct such a linear transformation. All right, so we define a function. All right, T from V to W, all right, as Tu equal to A1, W1 plus A2, W2 plus AN, Wn. Okay, so the AN, the coefficients are from the coefficients here. Okay. It is clear that this function meets our specification. It's clear that Tv1 is equal to T1 V1 plus 0 okay, so V1 has a unique representation of the linear combination of V1, V2 up to Vn. So this is the unique representation. And so the function value by definition is 1 and which is just W1. Okay? All right, and so we can do everything. The last one, so this is Wn. Right? So this function meets our specification. Okay, so it meets our specification. But we have to show it is a linear transformation. Okay? How? Well, we can apply theorem 2.4.c to show the additivity and these two formula and the scalar multiplication formula here. So we let V be another vector in V, and which is V1 plus V2, V2. Again, it has a unique representation V as V1, V2 up, a linear combination of V1, V2 up to Vn. So, all right. Then we have that U plus V, right? So the sum of this vector is equal to A1 plus B1, V1 plus A2 plus B2, V2 plus AN plus BN, BN here. Okay. So the addition of U and V has a unique representation as a linear combination of V1, V2 up to Vn. And the coefficients is just the sum of the corresponding coefficients in U and V. And what is alpha U? This is alpha A1, V1 plus alpha A2, alpha AN. Okay, so we have that. Okay, so we have, so they are unique representations, all right, as linear combination of V1, V2 up to Vn. Okay, now, so by definition, so now, and then T U plus V. By definition, it's A1 plus B1. We replace V1 by W1, okay? Okay, so this is from the definition. Of T, okay? And now we can split. So this is okay, plus okay. So we can split this vector into two terms. And for the first one, this is TU, okay, by the definition, and the second one is TV. Okay, so we prove the additive property. Okay. Okay, so by the definition of T here. And the T alpha U, by definition, this is alpha A1, W1, plus alpha A2, W2, plus alpha AN, WN, by the definition of T. Okay, and we can factor out alpha. And this is alpha TU. Okay, so from these two formula, so T is a linear transformation from V to W. Okay, so our construction is valid. Okay, so we justify that the construction here, this definition, give us a linear transformation from V to W and satisfy our specification here. So the only thing left is to prove that such a T is unique. That's theorem. I have to say that. Now assume that we have other linear transformation. Okay. From V to W, such that it satisfies our spec. Okay, satisfies spec. Then for all U, A1, B1 plus for all in the domain V, right? You know, in domain V, and every vector can be represented uniquely as a linear combination of V1, V2 up to Vn. So that the SU is equal to S A1 V1 plus A2 V2 plus plus AN Vn. Okay, and by linearity, this is equal to A1 X V1 plus A2 S V2 plus plus AN S Vn. But from the specification, this is equal to A1 W1 plus A2 W2 plus plus AN Wn. Right? And this one from our definition here is equal to TU. So we prove that SU is equal to TU for all vector U in the domain. So S is equal to T. Right. Okay, so the linear combination is uniquely defined. Any questions? So with this theorem, you can construct infinitely many linear transformations. Okay, because that you can use a different specification here, and there are infinitely many specifications you can put here, every specification gives you a unique linear transformation, and different specification give you different linear transformations. Okay, so VW are vector spaces, right? I will save time and a linear transformation. Okay, so T is a linear transformation from a vector space V to a vector space W. And if the index say U1, U2 up to UN is linearly dependent in V, recall that index say, for index say, it's possible that in the list, two of them may be equal, okay? So they may have repetitions of vectors in the list here, okay? If that is the case, that we find two members in the index say are equal, then this say must be linearly dependent, okay? I think you already know this. All right, so suppose that the index set is linearly dependent in V, then the index say, then we have a corresponding index say, W1, which is the image of V1, W2, which is the image of V2, etc., up to Wn, which is the image of Vn. This index set is also linearly dependent in W. All right, so it just says that a linear transformation will transform a linearly dependent index set into a linearly dependent index set. Okay? Proof. Since the index say U1 up to UN is linearly dependent, okay, there exist scalars A1 up to AN, not all zeros, okay, such that A1, U1 plus A2, U2 plus AN, UN equal to the zero vector. So now we have so we take the linear transformation which is T0 here. All right, and by linearity of T, this is A1 T U1 plus A2 T U2 plus AN T UN. Okay. But how about T0? T0 is T of 0 0. Okay. So you can think about it, the scalar 0 do the scalar multiplication with 0 here, and 0 times t0. Okay. Okay. And again, this is 0 vector. So basically, t0 is the 0 vector. Okay. So now we have, and this is implied as a1 w1 plus a2 w2 plus plus an wn is equal to the 0 vector. But they keep the same coefficients, and these coefficients are not all zeros. So this is which is a non-trivial linear relation on the index set. Okay, so this is a non-trivial linear relation. So that the index set w1, w2 up to wn is linearly dependent. Okay, so this is questions? Okay, so the theorems I presented today are very useful in our later discussion. So do you have any questions? So I hope you understand them well. Okay, so now I will go to chapter 3 about matrix operations. Actually, we talk a lot about matrix operations in chapter 1 and chapter 2. All right, so this is a short chapters in my lecture notes, because a lot of things I think you know a lot about it. So that a large part of the material will be a review only. Okay. All right, about matrices. We talk about the manipulation of matrices. So, well, I just want to review several things. Okay, so let A be an M times N matrix with rows R1, R2 up to Rm, because it has M rows. Okay, and we let B be an N times K matrix with this time columns B1, B2 up to BK. Okay, so A has M rows, and the B has K columns. All right. Now, a trivial theorem. I write it down. The ij's entries we call A times Bij of the product matrix A times B, it's just Ri. Ri is the ith row vector multiplied with the jth column for all I from 1 to m and j from 1 to k. Right? You all know that. All right, so that's I just write it down for your reference. We express A as column of row vectors, so that it's column of row vectors. So we have m rows. Okay, so we arrange the rows as a column, right? And we have k columns, and these k columns were arranged as a row. B1, BK here. Okay, so now the product, right? R1 multiplied with B1 give you the IY, the 1 entries of this product matrix. And this is R1, B2, R1, BK. And here is R2, B1, R2, B2, R2, BK. As we know, that those row vectors, column vectors are special types of matrices, right? Special. So these are metric multiplications. Okay, so a row vector multiplied with the column vector. And by the rule of metric multiplication, this will come to a scalar. Okay. Okay, and we have done. So that this one give us the formula. All right, so this is the one way to show how to do the matrix multiplication, right? This is one of the possibility. They are quite different, other different ways to do it. Okay. All right, so now we talk about the transpose. The transpose AT of a matrix A is the matrix whose ijth entry, whose ijth entry is the jth entry of A. So we know that the transpose of a matrix A whose ij entry is just the j entries of A. That is the definition of the transpose of a matrix A. Okay, so it is clear the transpose of A transpose is A itself. Okay? Right. Now, also note that we represent A as, when we represent A as column of, so this is M times N, as column of row vectors. If we have that, then the transpose of A, this is N times M. Okay? Then it will have M columns, so the transpose. And each column is the transpose of rows. Okay, so you can see that the A transpose has M columns. Right? Similarly, if we consider a matrix N times K and represent it as row of columns, B has K columns. So if we have B1, okay, I will borrow a few minutes from you because my class seems faster than the class in the classroom. B1, B2, and BK. Okay, so B has K columns here. So that the transpose of B, which has dimension K times N, so B transpose has K rows. And so their rows are transpose of the column of B. So this is B1 transpose, B2 transpose, up to BK transpose. Okay? Here, we have that. Now, so with these observations, we can write down a theorem. And you should know it before. The transpose of the product of A and B is equal to the product of BT and AT. So you have to reverse the order. Okay? And the proof is here. We know by the definition of the transpose of a matrix. What is that? By definition, this is what? This is AB of JI. Okay? And what is that? From the theorem here, the jth entries of AB is that is the jth row multiplied with the ith column of B. Okay, and it's a scalar, right? And so this can be written as BI transpose. So now we will let the column become to row and the row become to column here. Because the result is a scalar. Okay? So we have this identity here. And what is that? BIT is the ith row of BT. So it's the ith row of BT. And so this one is the ith row of B transpose. And what is this? This is the jth column of the A transpose. Again, by the theorem here, row multiplied with column give us the ij entries of BT80. Right? This is from theorem 3.1.1 here. Okay, and so you see all ij entries are the same, so that AB transpose is equal to B transpose and A transpose. And here. All right, so just reviews of some of metric manipulations we encountered before. Right, so I stop here, and you can take a break now, and the quiz examination will start at 11:20. So you have to make sure that you sit in the right place you are assigned. Otherwise, you will be considered absent from the quiz examination. Okay, and the TA will take pictures while you take the quiz examination.